Okay, remember that when you have a pile, the capacity is born from two components: the side friction resistance and the end bearing resistance. This is a tau and this is a sigma, right? So we know that if the condition is drained, then we use the beta method to get Fs. And the beta method is like this. Fs is equal to sigma prime V naught, right? The vertical effective stress in the middle of the segment in question. In here we have just one layer, so basically you would have your point here, right? Times K naught. This is the horizontal stress. Tangent of phi, and then Cm and Ck. So you know this. When do we use this? In the drain condition. That is in the short term for coarse and in the long term for coarse and fine. All right. So the next thing to do is to realize that if we have undrained conditions, for example, well, the only way we can have undrained conditions is in the short term for fine-grained soils. Short term for fine-grained soils, right? Long term, short term. So if we have undrained conditions, which only occur in the short term for fine-grained soils, then we use, to get Fs, we use the alpha method. Okay, this is the topic that we're going to be covering in this video. So you know how to use the beta method, you have examples, etc. But the alpha method is new. So what is the alpha method? Well, it's a way to get Fs. Beta method, Fs. Alpha method, also Fs. This is alpha times SU. Very simple. What is U? The SU of the layer in question. What alpha? Well, alpha is what we have to determine using the reader. So if you go to the reader, this is, I don't have any page numbers in my reader, sorry, but this is in inside the deep foundations section, obviously. It starts with 2, the number 2, and it says the undrained friction capacity is estimated by calculating Fs with the alpha method, etc., right? So this little chart here tells us, or plot, tells us what alpha should be depending on the SU of the soil. So for example, let's say that our soil, this one right here, is a clay with SU equal to 50 kPa. In that case, we go to the SU here, 50 kPa, alpha is 0.75. All right, so 0.75 times 50. Okay, sorry. So 0.75 times 50. So that's 37.5 kPa. Okay, so that's the method to determine Fs when we expect undrained conditions. Now, just a few comments about this plot here. Notice that the curve is basically made up of 3 lines. Okay, that's our way to simplify a curved data set. But the thing to notice here is that when the soil has a low strength, the alpha is high. And when the soil has a high strength, the alpha is the lowest that it can be, which is 0.5. So remember that this is for undrained conditions, and undrained conditions basically only happen in clays and silt. So mostly clays. So this is essentially a method for clays, even though it does apply to silts as well. Now, what happens is this: when the clay is soft or has a low strength, then it adheres very well to the pile, and this alpha is called the adhesion factor. So again, when the clay is soft, it adheres well to the pile, therefore the alpha is high. Conversely, when the clay is stronger, it adheres less efficiently to the pile, and therefore the adhesion factor alpha is lower, the minimum, which is 0.5. Okay? Now, below this plot, there is another plot. We're going to talk about that later on, so you can ignore this for now, this OCR alpha plot. So just concentrate on this top one. Okay, so let's do an example. Let's say that we have a pile that is resting. This is called a floating pile, by the way, which means that it's not on rock, but we'll talk about that later. Okay, so let's say that this is a high plasticity clay. The SU is 70 kPa. Let's say that the B is 0.3 meters. That's the diameter. Let's say that the thickness of this layer is 2 meters. Let's say that the added length here of the pile is 5 meters. Let's say this is a well-graded sand with phi equal to 35 degrees. And let's say the OCR is 1. And yeah, that's it. So here what we need to get is QS. That is the side friction capacity. Remember that the capacity has units of kilonewton. Okay? And we're going to say we're going to look for the short-term QS, the short-term capacity. Okay? Okay, short term. In the short term, the clay layer is going to act undrained, and the well-graded sand layer is going to act drained. So for this case, we have to use the alpha method, and for this case, we have to use the beta method to get the FSs. So let's get the FS of the clay. The Fs of the clay is alpha times SU, which is alpha times 70, right? And according to our plot, 0.55 for 70 kPa, 0.55 is the alpha. So 0.55, that's Fs. Now what's AS? The surface area of the segment that touches the clay, right? So that's pi b times the length, which is 2. For the well-graded sand, we use the beta method. The beta method tells us that we have the effective stress, right? Where's the point? Here. So this here is 2.5. 2.5 times plus 2 is 4.5. Where's the water table? Well, we're finding capacity, so we're in the design mode, so we have to put the water table right there, because that's the worst case. 2.5 plus 2 is 4.5, so this is 45, times K naught, which is 1 minus sine phi times OCR 1 to the sine 35. This is going to be 1 anyway. Okay, so that's K naught. This is sigma vertical, right? Tangent 35, which is phi, and then Cm Ck. So let's say this is a driven pile, right? If it's a driven pile, then it's low displacement. Therefore, this is 0.9, and it's a smooth concrete because it's driven. So 0.9. I think this is right. Let me check. No, driven small displacement. The value of CK is 1. Check your reader and you see that. Okay. And the AS is the surface area of the segment that touches the sand, right? This part. So this is pi b times the length of this segment, which is 5. All right, so let's get all these numbers here. Okay. Okay, so these are our numbers. Finally, we can get our QS. So what's QS? QS in the short term is the sum of FS AS, right? Which is FS1 AS1 plus FS2 AS2, which is equal to 38.5 times 1.88 plus 12.09 times 4.71. I hope you can see that. Yes. Okay. And what's all this? Let's see. This is basically 57, and this is 73 or so. Yeah. 72.5, but well, 73. So this is 130 kilonewton. That is the short-term capacity of this pile. Notice how we use the alpha method for the top layer and the beta method for the bottom layer. Because in the short term, this layer is undrained and this one is drained. Cool. Okay, if you go back to your first page here, or first part of the notes, you see that we said, yes, that the capacity, the full capacity is derived from the side friction resistance and the end bearing capacity, or end bearing resistance, sorry. So to get Fs, we have to use either the beta or alpha method, right? To get QE, we have to use different methods. So what we're gonna do is we're gonna start by getting QE, which is the end bearing resistance for, so this is the definition, or the name of it, okay, of this parameter. And what we're going to do first, and that is the topic of, or that is the last topic of this video, is that we're going to get QE prime for undrained conditions. Okay? Then obviously there's a QE prime for drained conditions. That one, it's a little longer, the procedure, so we're going to do it in class. But here we can do it very simple. This actually is very simple, so we can do it here quickly with a video. So QE prime for undrained conditions. Again, the pile, QE prime. All right. So if you go to your reader, let me just get the reader. Okay, here's the reader. You'll see that there's a page very close to the previous page that says the foundation's end bearing capacity. Okay, the top portion is associated with the QE for drain conditions. So you can ignore this part. Okay, so don't worry about that. Just go to the bottom, and on the bottom you'll see this plot. Okay, and you can see here that it says the undrained QE prime end bearing resistance is calculated with knowledge of SU, as QE prime is SU NC star. Okay, and NC star is dependent on SU. So it's very similar to the alpha method in the sense that you multiply the SU times some parameter that is dependent on the SU. In this case, it's called NC star. So depending on the SU that you have, where? Down here, in this area, depending on that SU of the SU of the soil in this area, or in that zone, let's say it's, I don't know, 90 kPa, then your NC star is 8.75 in that case. Okay, just like the alpha method, this plot or graph comes from experiments that were plotted, right, and then a trend was fitted so that we can then use it for our designs. All right, so that's, I mean, it's very simple. So whatever the soil is down here, in fact, this zone is 2B below the base. Now, B for a pile generally is not that large unless you have a very, very, very large pile. But let's say for a 1 foot diameter pile or so, it would be 2 feet, right? The zone would be 2 feet. So in any case, that influence zone, which is 2B below the base for capacity, end bearing capacity of a pile, or end bearing resistance to be more correct here, okay? That is the zone that you are going to evaluate the SU at. So very simple, right? What do you do? Well, let's do an example. In fact, we can just do it right here. Let's say that you have a pile. This pile is 7 meters long. Let's say again that the B is 0.3 meters and it's a driven concrete pile. Okay, and let's say that now the top here, let's say this is 5 and this is 2. Let's say this is the sand and this is the clay. Okay, and the question is determine the end bearing resistance for the pile in the short term. Okay, solution. All right, in the short term, the end bearing, which is this portion here, this zone, is in the clay. Therefore, this zone is going to act undrained. So we need to use the NC star method. QE prime is equal to NC star times SU. Oops, I forgot to give you parameters here. This could be phi equal 30, SU equal, let's say 50 kPa. Okay, so you would be given this. So the question is, what's QE prime? Short term. Okay, in the short term it's undrained because this is a clay, right? And therefore we get NC star times SU. SU is 50. And what's NC star? Well, if we go to the reader, 50, NC star is 8. 8. So this is 400 kPa. That's the answer. Very simple. Now, you may say, well, what happened to the other QE? some people generally tend to ask, what happened to the other QE, the one associated with the sand? There's no other QE, there's only one end. There's only one end to the pile. Whereas for side friction, there could be more than one FS, obviously. For example, in this case, we have two FSs. But there's only one QE always, because there's only one end of the pile. Okay? Now, to finalize, another question would be, what is the end bearing capacity? This is the end bearing capacity. The end bearing capacity is the stress times the area. Just like we have QS equal to FSAS, we have QE is equal to QE prime, end bearing resistance, times the area. Well, this is a sigma, right? So what's the area associated with that sigma? Well, it's the end bearing area of the pile. So it's not the surface area, it's the end bearing. It's normal to the sigma, normal to the QE. So this is pi r squared. So for our example, QE is equal to QE prime 400 times AE, which is pi 0.3 over 2, which is the radius squared. And what's this? .3 kilonewtons. That is the end bearing capacity, kilonewtons. Now, and that is in the short term. Short term. Right? We are evaluating in the short term. So finally, your capacity of the pile is the side friction capacity plus the end bearing capacity. Okay, so you would have to be able to get this one, or to get this one, you would have to do the same thing that we did for the previous example, right? But now considering the different layer thicknesses, etc., segment thicknesses or segment lengths. Okay, and then you would add to that capacity the end bearing capacity, which is 28.3. This is the capacity of the pile in the short term. Simply the summation of the side friction capacity and the end bearing capacity. Okay. Oops, there we go. The ultimate is the so-called the full capacity. Remember, in the short term. Why do I write short term? Because that was the question, right? And so we proceeded to use the short term equations that are relevant to clays in the short term, which basically are the undrained equations right here, the undrained equation 1. Okay, so this is the answer that we got. We would then sum the side friction capacity if we had it, or if we calculated it. You can do it. In this case, you would use alpha for this layer and obviously beta for that one, right? Then you add and get the ultimate for the short term. Total capacity is the side friction capacity plus the end bearing capacity.